Good morning. If you remember anything from the talk that I gave 2 days ago, and by the way, it might seem like 2 weeks ago, but it's only 2 days, it's that materials are the pacing item for the commercialization of LENR, okay? And we need reactors, and we need something to put into reactors. It's entirely similar to burning fossil fuels. You need a furnace and you need the fuel, okay? So we are looking for the development of generators, but wait, we have companies now that are working hard to develop generators, okay? But how many companies are working hard to develop materials that will perform adequately? That's a fewer number, and that's why we're in the process of developing a major materials development program for the commercialization of LENR. Now, I should have a graph for this, but I'd ask you to imagine a plot that has power vertically and time horizontally. Now, the time axis is months, because if you have an LENR reactor, you want it to work for a while. Days isn't sufficient. Months might be okay, years would be better, okay? But there's a problem in how long it'll last. I'll come back to that. Now, vertically, the power axis, watt, 10 watts, 100 watts, kilowatt. I'm offering the viewpoint that there's a line at the kilowatt level, okay? And that's there because when you get a reactor that produces more than a kilowatt of thermal or electrical heat, okay, then you can sell into the home market. It takes kilowatt or a few kilowatts to run a home, and that's like a magic barrier. So I'm looking for some company to produce something that lasts long enough, of course, but also puts out over a kilowatt. Now, I'm old enough, I remember the 4-minute mile. There was a time when, could humans run a mile in 4 minutes? And finally, a Brit, I think, Roger Bannister, broke the 4-minute mile. I remember his name because it was such a big news event. So I'm looking for somebody to break the kilowatt level, okay, in something that lasts long enough. And that's what we're working towards. So I have questions for you. What is the silicon of LENR? If you look back in the history of semiconductors, early on it was recognized that silicon would be useful. A lot of other semiconductors, gallium arsenide, gallium nitride, many things have been developed. But the computer revolution, the internet revolution, and the AI revolution have all been based on silicon. So I ask, is there such a material yet for LENR? Is it known? I mean, are any of you working with it, or is it something to still be developed? In my mind, that's an open question. We don't know the answer to that, and that is pivotal to the development of an LENR industry. Okay, so the materials challenges are a reliable operation, of course, related to reproducibility. Controllability. It would be really nice to be able to turn the power from an LENR generator up and down. Of course, we want high power output and long-term operation for commercialization. Now, at the bottom is something that, in a way, but it doesn't get the attention that it deserves, so I'll spend a moment on it. Diffusion is good. As Ed Storm said, one of his key steps is the motion of the reactants, be they deuterons or protons, from wherever they start to the nuclear active environment. So that's really good. Well, but diffusion is bad. It doesn't happen instantaneously. It's not like the motion of gas through a porous material. It takes time, and that has to do with the response time of the system. You turn the knob, and how fast does the temperature change? But more important than that, in my mind, is it can destroy the nuclear active environments, to use Ed's terminology. Okay? If you need small gaps, and the atoms are jumping around, and they will heal them, we know that from sintering data, okay? What can be done? Okay, so that's a driver in our view of this world. Now, this paper is a review paper. It's focused on titanium because there's been a lot of work on titanium. It's basically a homework step towards the development of the program that we're hoping to be able to do. So for completeness sake, I include the phase diagram. I'm not going to spend any time on it. Significant time. It shows atom percent hydrogen horizontally and the temperature vertically, the various phases. A lot is known about the titanium hydride system from many years of work. And my colleagues, Emma Morano, he's somewhere here, and Ashraf Imam, we're all material scientists. Imam's an internationally known expert on titanium, so that's why we're looking at titanium. Here is more information on the phase diagram. I'll skip what's on the top. On the bottom is an image of a roughly centimeter diameter disc that started out being pure titanium, was loaded with deuterium. It changed from a hexagonal closed-packed titanium structure to a face-centered cubic hydride structure without falling apart. It cracked, but it doesn't fall apart. So we know a lot about titanium already. And you might say, but Dave, what about titanium and LENR? So here's a plot of the number of papers per year versus year that involved titanium in the LENR literature. I got this from Jed Rothwell's site. And you see it falls into three groupings: immediate high interest, then a declining interest over a number of years, and finally there's just a scattering of papers now. So why was there initial great interest? Let's see. People listen to Fleischmann and Pons. They envisioned a world run by LENR power, and then they looked at the price of palladium. Okay, so he started working at titanium because it's known that it will soak up a large amount of either deuterium or hydrogen. 2 deuterons or protons per titanium. It has a very, very high density. So great initial interest. Why did that interest go away fairly quickly after the first 3 years? And it's probably because despite a large number of experiments, and you see a large number of papers, well over 100, good results weren't obtained. People didn't get high output energy from them, so the interest declined. But there's a large database on the use of titanium for LENR experiments. They included various types of loading and excitation, electrochemistry. Also, there were experiments on thermal shocking. They would have a vial, Scaramucci and others, titanium shavings, and then they would pour liquid nitrogen in it and look for neutrons, things like that. Many attempts to measure neutrons. Over 30 papers reported that you could measure neutrons from titanium. Okay, some of the experiments were done in mines. It was very good work. A few of the experiments resulted in tritium measurements, and there were a few, very few experiments that resulted in transmutation data. So that's the kind of experiment that was done for titanium. Now, I thought about showing you graph after graph after graph of data. Okay. And fortunately, I restrained myself. But there is one here. I asked myself, what's some good excess heat data from titanium experiments? And you see here an experiment done by John Dash and his student Warner. Heat produced during the electrolysis with D2O of titanium cathodes. And they started out with a 0.5 millimeter thick titanium foil. They rolled it, cold worked it to various levels. So on the horizontal axis is the percent reduction in the titanium thickness, and vertically is their measured LENR heat. And you see it only goes up to about 0.4 of a watt. But there's a trend. It starts out lower, increases with the cold working, maybe due to the formations of dislocations and grain boundaries and things, and then eventually it rolls over and declines back to being useless. So there's some data like this available. It's very interesting intellectually, probably important scientifically, not necessarily important in terms of commercialization. So if you're formulating a materials program to systematically make and measure materials to find out what is the silicon of LENR, there's a starting base. I went to Rothwell's library. It's got close to 5,000 entries. It searched on palladium, got 1,000 hits. And one out of 5 papers in the field have to do with palladium. Titanium, many fewer. Nickel, still a lot fewer in alloys. So anyway, this review of titanium should be, and we hope to accompany it by a similar review of work on nickel for LENR experiments and alloys for LENR experiments. So we're in the process of, you might say, doing our homework. Okay. Now I'm going to do something a little strange here. It's a scientific conference. It's not a commercial conference. But the issue of price of the reactant materials is really important. It may determine when LENR generators come to market. It may influence market penetration after they come to market. We don't know. So this is a plot versus years horizontally, and it shows the prices of palladium in orange and then also platinum and gold. So very expensive material. It's down to only $1,000 an ounce right now. That's what the little arrow on the right indicates. Now, I'd be interested in how many of you have been involved in discussions about recycling palladium from LENR generators. I'll get to that momentarily. Okay, so in order for palladium to be useful in commercial LENR generators, we have to have enough palladium to meet available demand, and the cost of recycling, the processing cost, the loss cost, and so forth has to be manageable. Now, thinking about recycling palladium from LENR generators led to me to thinking about catalytic converters for cars. They contain about 10 grams of platinum, palladium, and rhodium. The value is anywhere from a few hundred to a few $1,000s. Recycling is routine, as you know. There's valuable enough to be stolen. Okay, so I've done some estimates of the possibility of recycling palladium from LENR reactors, and it's not insane. It could happen. Okay, but one of the problems is the amount of palladium. I'll get to that in a moment. Now, there's an experiment that Preparata reported in 1996 where he had a 2-meter-long spiral cathode and did electromigration, and he reported 50 kilowatts per cubic centimeter. 50 kilowatts, imagine a sugar cube, 50 kilowatts. So if a 10 kilowatt system for a home was based on this, you need only 3 grams of palladium, a practical amount. Now, I would add in the bottom here that this experiment has not been reproduced, and it was electrochemical. It's a scientific experiment, but hopefully we can find a way to reproduce that. Now, shifting gears to the prices of nickel or titanium, if they turn out to be the silicon of LENR, you see you have a dramatically different price point. Okay, and when you get to the production, the worldwide production of palladium is about roughly 200 tons, and about half of that is recovered from catalytic converters and other things. Fairly small number compared to the annual production of titanium in the middle, 3 million metric tons, and nickel at the bottom, 3.7 million metric tons. So the two conditions you need, you have to have enough, and then you have to satisfy the economics. There's a question in my mind that even if the economics work for palladium, there might not be enough material. Okay, now I make a comment in passing. Constantan has been used by Chelani, Alexandrov, a few others with great effect, and it's a material that's sort of in the lead for looking at what might be the most important for material for LENR. So my conclusion is very simple. There's been promising work done with titanium, but it has to be augmented. Okay, we need much more research on that. Now I'm going to do something that is a little strange. When I prepared this talk, I had in mind the reprocessing of LENR materials. Now Ed Storms mentioned that. Okay, and if you go back to Arata's papers, he had a paper where he was concerned about helium plugging up the palladium as a function of time and destroying the efficacy from an LENR viewpoint. So Ed's point was very well made. Do we have to renew materials for practical LENR generators? Now, Mizuno had the idea that you have 2 side-by-side reactors, you run one and then renew the material in the other offline. So at the time I prepared this talk, I was not going to go public with this, but I've changed my mind. So I'm introducing a concept for in situ renewal of LENR materials in practical reactors. Okay, and there are lots of ways you might do it, but most of you know what ball milling is. You have a chamber, you have balls, commonly steel balls, sometimes carbide balls. If you put in there and you turn it over with a brittle material in there, it gets broken up into fine pieces. So I'm now contemplating and offering you the opportunity to think about the possibility of using ball milling as an online way to renew LENR materials. Now, it could be done 2 ways. You might want to tilt the reactor and have the powder. Nanomaterials have been shown by the Japanese work and now by what John Paul is doing and his colleagues to be very beneficial. Okay.
5 minutes.
Thank you, sir. So I'm imagining an LENR reactor that contains fine-scale materials, and it runs, and it is running down. Helium is clogging up the materials. The active NAE are being destroyed. So then you'd essentially remove the powder from the reactor, again, mechanically, automatically, a machine, okay? And then put it into a ball mill to break up the particles, to liberate the helium, to renew the NAE, the nuclear active environment, and then reintroduce it into the reactor, okay? Or maybe even the ball mill is the reaction chamber. If you're using a hot gas experiment, or maybe even a plasma experiment, you don't have to move the material. You run it for a few minutes in order to renew the material, and then continue the use of it. Okay, so when I prepared the talk, I wasn't going to talk about that. I was going to seek a patent on it. I changed my mind, so I'm throwing it out to you for your consideration and discussion. A challenge to inventors in the room. There's an inventor back there. Okay, to design a system that would allow the in situ renewal of active LENR materials for a long time commercially profitable operation. So thanks for your attention. I very much appreciate it.
Any questions or comments? Yeah, please.
Alan.
When I found the switch, were you there? Yeah. I was very interested in your comments on ball milling, because that is a branch of chemistry now these days called mechanochemistry. Yeah, the use of physical motion or whatever, energy, stirrers, grinders. And it can achieve things that normally have only been done in very messy wet chemistry processes. You can make things happen, as it were, with mechanochemistry. Very interesting. Another point about materials, I think, like particularly titanium and possibly aluminium, which Jean-Paul has had some success with the LEC, is that the surface is very prone to oxidation. And one of the effects of certainly of the oxidation of an aluminium surface is that it becomes a pseudo diode, as it were. It becomes a semiconducting surface, and I have a feeling that this is actually an important feature of some materials, that when they're in the semiconducting state on the surface of the cathode perhaps, then they are more readily activated. Yeah.
Yeah, thank you. We have a flash sintering process that starts with nanometer and micrometer scale powders in order to make chunks of material that can go into reactors, now, related to what you just said. Thank you. Francesco.
Okay, just a comment. There are not only the true Constantan whites like Demeter or mine, but most of the powders are made by nickel copper, and the experiment of Iwamura Clean Planet are nickel copper. So nickel will be largely used. So not only true Constantan, but okay.
Yeah, I appreciate that comment, because if it turns out that nickel is the silicon of LENR, or a nickel alloy of some kind, that would be a very, very beneficial situation, because there's a lot of nickel relatively.
Okay, thank you.
Robert, Bob?
Thank you, David. We've heard from Engate, who are doing a plasma vortex reactor, and those typically are using metal nanoparticles. Now, Klimov, which is probably the progenitor, the originator of the modern plasma vortex reactor, recently in a presentation has suggested that as much as 2 and a bit decades ago, they've removed the metal from the equation, and they're using carbon nanoparticles produced by insertion of propane in there, and carbon would therefore be the fuel. This negates any necessity to recycle anything.
Okay, I am not 100% clear on why that would be so. I mean, the carbon may suffer from the same problems of product buildup and destruction of the NE and so forth as do other materials, metallic materials. So I say I'm not sure.
Yeah, so in his reactors, the metal becomes part of the plasma vortex, and it's consumed and transmuted, observed by many different means anyone could expect to see. But they found that actually the same kind of levels of excess heat could be produced by the use of actual just carbon.
Yeah. So even though I don't really understand that, I recognize that in the long run, you know, you go down the road 20 years, no, 50 years, and we're all using, you know, LENR reactors are everywhere. You know, they could be carbon-based. We don't know.
Mm-hmm.
Okay.
Okay, thank you, David.
Thank you. Okay. Thank you very much.
Thank you.